Thank you very much for joining here this presentation. My name is Jens Merten. I'm from CEA. This is a French big research organization of 20,000 people, and we are looking into new concepts of distributing electricity. And the concept we have developed, we feel that they are very well adapted for data centers. The co-author, Boris Sučić, he is not available, but he is in Slovenia and he will realize a data center with this new concept which I am talking about. Actually, the new concept is based on increasing the voltage of distribution inside the data center to medium voltage levels. This is something very new. Normally, the distribution is triple phase, 400 volt AC, something like this. What we want to go to, we want to go to 3 kilovolts, plus minus 1.5. You will see this. Actually, why do we want to go there? Well, there is a lot of electricity demand for data centers, and we can gain efficiency with this new concept. And also, when you have a look at the top reporting priorities which are identified for data centers, this new concept is actually addressing a lot of these points here, especially the scope 2 emissions. So what is the concept? The concept is that we use a medium voltage DC grid to distribute the power to the racks. So at the input we have a standard transformer, then this is normal, then we have an active front end. Actually this is a big rectifier which is producing a medium voltage DC grid, and this medium voltage DC grid we decided to use a medium voltage DC grid which is plus minus 1.5 kilovolts. Why this value of 1500 volts? Because actually a low voltage grid is 1500 volts and a lot of protection devices are available for this voltage level. So what we are doing actually here in order to increase voltage is to combine in series two low voltage DC grids. So we have one DC grid at 1500, another one at minus 1500, we combine this and then we can power the servers with 1500 volts. The advantage of this is that you gain a lot of flexibility, modularity, and reduced planning efforts. So you also gain in efficiency. So you can see here the battery. The battery is directly connected to this grid. And when the battery is not used, we do not ship energy through two converters in order to get the data center running. This means a gain in efficiency. Furthermore, there's also an interest to green a little bit the data centers. And we can green data centers with direct use of solar energy. If we have a data center, a lot of surface around, we can set up PV power plants, and we can inject the energy of this PV power plant directly on this DC bus. By this way, the number of conversions will be reduced and the PV energy is directly used by the servers. Now we have this medium voltage grid of 3 kilovolts, and we distribute this in the data center. I showed here just one power box. So there's one power box which takes the 3 kilovolts and puts this down to 400 volts DC, which is a normal handleable voltage level, which then can be used by the power shelves in the racks. So the OCP racks, this is standard racks, and they are powered not with AC, but they are powered with 400 volt DC or 380. It's the voltage level which is well adapted, and there are already commercial providers who can offer these power shelves. for example, Murata. So this is the concept. It is very simple. It is different. It is new. And it's promising a lot of advantages. The first thing, as I told you already, we avoid the losses in the UPS. There are 2 conversion steps. We avoid these conversion losses. Also, as we increase the voltage drastically, we also drastically reduce the current. And the current losses, they go with the square of the current. So this means we have really reduced losses, and we also have less copper and aluminum cables inside the data center. Yes, and the other point is, of course, the power shelves themselves. The power shelves themselves in the long term can be reduced in volume, because actually these power shelves, these are power supplies which are powered with AC monophase. And this means that there's always a current ripple which has to be reduced and minimized by capacitors. And these capacitors, they are an element of insecurity and failure, but also they take a lot of volume. So if these power shelves, they can be optimized for DC, they will reduce volume. So less filters, less volume, less costs, more reliability. Another point, when you are setting up data centers with a lot of power shelves, you will have harmonic injection into the AC grid of the data center. And this is also a problem which is occurring, and it's very difficult to plan, and you have to put a lot of filtering inside the power shelves in order to limit harmonic injection, which then will lead to unstable systems. All this filtering is not needed anymore with this DC concept. So here, again, a factor to reduce volume. There's also no reactive power. This does not exist with the data center in DC. Flexibility. We are more and more flexible, because as we can plug more racks or less racks, it is very, very flexible. We can put, once a data center is designed and installed, it is even possible in a later stage to add additional consumers or PV systems or batteries. Everything is very modular and flexible in the design. If you have a look at the conversion losses, on the left side you have the approach of today. So we have the grid, then there's online UPS, so we have 2 times 2% losses there. Then there's a separation transformer. Then it goes into the power shelves. Here we have 3% for the power shelves. And then the green box, this is the rack. There are the power shelves with 3%, and then it goes to the microprocessors. So here, this is what we have today. And we see that for the grid power, when we sum up all the losses, it's summing up to 14% the losses. This is also the case for the PV energy, which might be used. So if we use PV energy, we have to inject this on AC side and with a converter. So the concept looks very different when we use a medium voltage DC grid for powering the data center. Here we have the grid, we have the active front end. The UPS is now line interactive. The PV converter has a better conversion efficiency because we do not have to have the hassles with AC. There's the MVDC bus 3 kilovolts. There is one converter which is producing the 400 volts. It's the power box, and then it goes into the rack, and there is the power shelf powering the servers. So when we sum up all the losses, now we are for PV energy, for example, we add at 4% instead of 14%. So we really reduce losses. So it is an interesting concept. It is very new, And we have a European project which is called the DC Power, and this DC Power project started in January, and there will be a pilot data center set up in Slovenia. It will be done by Joseph Stefan Institute, and they preview 2 phases. In the first phase, they will do 500 kilowatts. In the next phase, they go up to 5 megawatts. There will be a lot of high-performance computing in this data center. The excess heat they want to use directly by the nearby buildings, and this medium voltage DC grid will be implemented in this data center. In order to check the gains, which we are claiming, a comprehensive measurement and verification plan will be set up. So here you can see, well, it's just in the moment it's a computer graph, and the MVDC power system will be monitored with several meters, 15 meters, will accurately monitoring all the energy flows in the bus in order to see what in the end will the real gain in efficiency. And in parallel, an AC powered system with the standard architecture will be also set up and monitored. The approach then is to use these 2 phases, and these 2 phases, it's to test these 2 options and to compare the efficiency achieved. One will be the MVDC architecture, and there will be 3 voltage levels. There will be the 3000 kilovolts medium voltage for the long distances. Then there will be a power box, which is then going down to 400 volts to power the racks. And then there will be, inside the IT racks, there will be the power shelves, which go to 54 volt or 48, what is needed by the servers. This will be the first architecture to be studied, and the second one will be the conventional AC architecture. So, and then this measurement and validation plan will determine what are the energy savings realized, and for this specific data centers, the energy savings expected are between 1.6 and 2.1 gigawatt hours per year. So as a conclusions, the time is over, I hurry up. Well, standard power supply architecture of data centers is something which really needs to be improved, especially when we go to high power racks. Medium voltage DC grid is a more efficient and more flexible solution to do this. And actually, what we don't need to do is we need a holistic approach for powering data centers. So from the grid to the servers, the whole view is needed. So a data center will be set up as a pilot in Slovenia, and there is a lot of expected energy savings for this. So call for action. What is the problem to solve? Okay, let's improve efficiency. Let's test the medium voltage DC architecture. If you want to get involved in this, please take a photograph of my email or contact me after the meeting. I will be very happy to discuss with you all these aspects. I'm not a data center expert, but we are very interested in bringing medium voltage DC grids also into the data center world. Thank you very much. As the next speaker is not coming, I'm open for question.
From a safety perspective, more DC, direct current, is there any challenges from a safety perspective that you guys foresee?
Yes, there are from the safety perspective, we need protection devices which are well adapted to these medium voltage DC grids. And these protection devices are, this is a point because they are very expensive in the moment, because they are only available for railway applications. And the power level of the high railway applications is very, very high, and so they are usually oversized and so very expensive. But we have to start things going and start something. Well, I do not want to take the time of the next speaker, if it's here. Okay. So I hand over the microphone. Thank you very much. I'm available for discussions here.